We have Alexander from Brigham University in Miami doing what I hope is a pun intended coherent introduction to mirror symmetry.
Yes, I was telling some of the guys before you got here that the more that I thought about it, I may not get quite as far as I hoped. But anyway, so it's going to be kind of, the first part is going to be a pseudo-historical introduction. Don't take it too literally, but it's like a little fairy tale about how mirror symmetry, one avenue through which it was observed. And then whatever time we have left after that, we'll be trying to get a little bit hands-on with the homological side of things. Okay, so, right, this is a little, I feel a little bit guilty about the title now, considering we might not get quite as coherent as I planned. But anyway, let's just see that where we go. Let's get mirror symmetry. Okay. So, like I was just saying to the people who were here a little bit early, the algebraic geometers in the room might be a little disappointed, but such is life. This is going to be pretty from the ground up. So what is mirror symmetry? Like the goal that I have basically is to, if you haven't heard of it before, give you an idea of like what people are talking about when they say that. So it originates in some sense in physics, in string theory. So in string theory, there's many different versions, of course, whatever, and I don't know physics, so don't even bother. But the space-time is supposed to be not just the standard R4, but instead it's R4, right, time in the 3 space dimensions, along with some so-called compactified dimensions, here x, where x is a, quotes, very small, compact 6-dimensional manifold. Okay, so many of you may have seen this picture before, but the idea is, like, you think it looks like this, right? Maybe this looks like R, but actually if you zoom in, it could be that it's like a hose that you're looking from far away, right? So this is actually R, process 1. Okay, so that's the starting point, and it turns out that this, again, ask the physicist, this X can't just be any compact 6-dimensional manifold, it has to be what's called a Calabi-Yau threefold. So X is actually Calabi-Yau also. So the first part I'm going to try to explain, again, without assuming too much background in complex geometry, what that means, what are some examples of it, what does this entail? Okay, so X is a Calabi-Yau manifold. So I have to say what a Calabi-Yau manifold is. So, among other things, first of all, X has to be a complex manifold. Okay. So what is a complex manifold? So it's locally homeomorphic to some open subset of Cn. Standard thing we mean when we talk about a manifold, right? It looks like, in this case, instead of Rn, it's Cn, and then we also impose the condition that these transition functions are homomorphic. So if you haven't seen this before, what we're looking for is, here's some x. For every point, you can find some, basically what we call a coordinate neighborhood. And the idea is that if you choose different coordinate representations, so like phi1 and phi2, this here, this phi2 of phi1 inverse should be homomorphic. So it's kind of an upgrade of a smooth manifold, right? We require more of these charts. Okay, so it's something that locally looks like Cn, right? So many of you have surely seen this before, but just trying to keep things fairly complete here. So first of all, X has to be a complex manifold, and we would say a complex 3 manifold, because if it's a 6-dimensional real manifold, it's going to have to be a C3 here. So, where are our erasers? What else? So that's the first thing that this entails. The The second thing is we're going to require, there's a very convenient class of complex manifolds that people like to talk about, which is that, okay, so we already said X is compact. It's also what we call a Kähler manifold. Okay, so Kähler is just a very nice class of complex manifolds where basically we have compatible complex, symplectic, and Riemannian structures. Okay, so what I mean by that is, okay, so I'm already starting to condense things, but by the complex structure, I mean some choice of charts here up to the natural sense of equivalence, some atlas. Symplectic, okay, so I think everyone was here from Mohammed's talk, so we at least in principle know what this word means. It means there's a closed, non-degenerate two-form called omega. And a Riemannian manifold has a metric G. So Riemannian metric G, which takes, I guess you could say it's a section of this. Okay, so I have to say what compatible means, but the point is on a Kähler manifold, it's a very nice geometric setting because there's a lot of things we can work with, right? We have a complex structure, first of all, so it looks locally like Cn in this way. And it's a Riemannian manifold in the sense that we have this metric tensor that allows us to talk about distances and angles and all the usual things that ideally when we talk about geometry, we have these notions. And then it also has this symplectic structure, which I'm not going to get too into the details of what we need that for, but at least on a intuitive level, it's giving us some way of talking about two-dimensional areas. It's two forms, so it takes two vectors and gives us an area. And what do we mean when, so lots of things we can say geometrically on such a manifold. What do we mean when we say that they're compatible? We're just saying that, okay, so G, our metric, let's say, so that takes two tangent vectors in, should be the same as, I'm going to have to elaborate on this a bit, whatever this symplectic form does to this pair of inputs, and now I use this J that I haven't specified yet. So I should add one more note. When we have a complex manifold, a very useful alternate point of view is that on each tangent space we have a notion of what it means to rotate by 90 degrees or multiply by I. So this J is supposed to be not M, X. This J is a map from each tangent space to itself. That when you square it, you get -1. Again, this is just abstracting the notion of multiplying by I. This is known as an almost complex structure. I'm doing things a little bit out of order or messily here. But the point is that any such complex structure, of course, we know if our manifold locally looks like Cn, it makes sense on the tangent space to multiply by I. This is a slightly more general notion because on a real or smooth manifold, we might have such a map. And then if they are what's known as integrable, we have, in other words, if these fit together in the appropriate way, in other words, if it comes from a global complex structure, then we say it's integrable. There's various conditions for this in terms of some PDEs. Not really relevant to us, that's why I'm kind of skimming over it. But this is just one way of saying, there's much more you could say about this. All three of these different structures, the G, the omega, and the J, right, the complex, the symplectic, and the Riemannian all play together nicely. That's all we really need. And even that, considering we're not going to prove a whole lot today, we don't strictly need, but I just want you to have a sense of what the word is referring to. Right? So Kähler is a particularly nice class of complex manifolds. They come up a lot. And they're going to be the ones that we're particularly interested in. So now, I've said ultimately our goal was to describe what a Calabi-Yau manifold is. They are complex, and within the class of complex manifolds, they are Kähler and compact. So what else, right? What else do we need to specify? One more thing I should say before we move on. I would be not living according to my values if I didn't say at least a couple of examples. So what are we talking about? Okay, so first of all, complex manifolds, many of them are familiar, are things like Cn, of course, the complex projective space, smooth algebraic varieties. And when I say varieties, I just mean, let's take it in the most down-to-earth sense, solutions to polynomial equations in some Cn or CPN. So not complex, maybe complex manifolds S6. This is a famous open problem that we know that S6 has an almost complex structure, but it's still not determined whether there is a complex structure. And then no, again, if you haven't seen much about complex manifolds, RP2 is not a complex manifold, no matter what charts you pick, because it's not orientable. You can show pretty easily that any complex manifold is orientable. And then S3, of course, isn't for dimension reasons. Any complex manifold has to be even real dimension. And then as far as Kähler and not Kähler goes, within the class of complex manifolds, okay, so most of the things that, like the nicest things we come up with are Kähler, for instance, the most important class being smooth projective varieties. And these are Kähler basically because CPN is Kähler, and it turns out that any complex submanifold of the Kähler manifold is also Kähler. And then not Kähler, this is, I just say it for the sake of defining the boundaries a little better. It's not really super relevant to us. Talk about Hopf manifolds. Originally, I was thinking maybe to say what that is, but we're not even going to think about these anyway. But if the term comes up, right, you know, there are some interesting complex manifolds that aren't Kähler, and actually, maybe I should say more relevant. Some complex tori are not Kähler. Complex tori, I mean quotients of Cn by the lattice. Okay. All right, so we're going a little bit speeding through this. If you haven't seen complex geometry before, it's probably not super, not the best introduction, but just to get our bearings, right? The point is, we're trying to describe, okay, what is this Calabi-Yau condition, right? X has to be a complex manifold. It has to be a particular type, and now I guess I've earned the right to say what the last condition is.
One question.
Yes?
When you say some complex tori, is it depending on n, depending on the lattice?
It depends on the lattice. There's a so-called like polarization condition that the lattice has to satisfy. So in every dimension n, you have some of the complex tori are Kähler, others aren't. Well, except dimension 1, they all are.
Okay.
I guess maybe that would be a reasonable add-on. Like every complex curve or Riemann surface is Kähler. That's nice for us. So every Riemann surface is also in this particularly nice class where we have all these different geometric structures playing well together.
And it's in the one is Kähler.
Oh, yeah. Let's see, we're gonna just do a lazy thing. Okay, so the last bit we need to even really start the discussion is what does it mean to be Calabi-Yau? So we want our we want a complex manifold. We want it to be Kähler, and then the last thing is that the so-called canonical bundle is trivial. Again, I'm allowing myself a little leeway because Andreas talked about what vector bundles are, so I think it's, I'm just going to assume it's fair game to have the notion of a vector bundle. What do we mean by the canonical bundle? Like the canonical bundle, so I have to introduce a couple of things, but they're not too bad. So on a complex manifold, we can talk about not only n-forms, but we can talk about homomorphic or anti-homomorphic n-forms. The complex structure gives us a way of saying which functions are homomorphic or not. So by this we mean the homomorphic one-forms. Or not the one-forms, those are the sections. This is the homomorphic tangent bundle. So I'm being a little bit sketchy here because I'm not defining all these things from scratch because we wouldn't get to what I want to get to. But in any case, you can imagine, even without a strict definition, that the complex structure gives us some way of saying what is homomorphic and what isn't. So we can, if we're talking about, for instance, vector fields or one-forms, we can say, oh, these are homomorphic as a special subset of all of them. So in the tangent bundle, we have a sub-bundle that consists of the homomorphic part, and I can talk about the homomorphic cotangent bundle, and then I can talk about the homomorphic, here let's say dimension of x is n, homomorphic n-forms. Okay. So again, because I'm being rather quick with this and not giving every definition, this is our so-called canonical bundle. Is the canonical bundle. What is it? It's basically, one way to think about it is the locally, its sections are homomorphic volume forms, things that look like f dz1 up to dzn, and is the dimension here, where here z1 through zn are some kind of local coordinates. So again, this is definitely not a replacement for like actually learning the basics of complex geometry, but hopefully it's enough to keep the thread going. In the same way that on a real manifold, you have local coordinates, x1 through xn. On a complex manifold, we have z1 through zn. And we can also talk about about z1 bar through zn bar. If you look at the entire cotangent space, all the dz1s through, and all the dzis and dz bar i's span the cotangent space, and so these are precisely the things that you need for this exterior power. So the buzzword that you might want to think about is homomorphic volume form. So just to be clear, this is not a volume form in the usual sense because it doesn't have the right, like if X is an n-dimensional complex manifold, it's a 2n-dimensional real manifold, smooth manifold. So a volume form in the traditional sense is a 2n form, and this is an n form. But like omega wedge, omega bar would be a true volume form. So the homomorphic volume form, what do we need with that? Okay, so this is what the canonical bundle means. It's literally just things of this form, locally at least. And for a Calabi-Yau manifold, we want this bundle to be trivial. In other words, sorry, there's a way to trivialize it. So why is that an interesting condition? basically, we can think of this as a sort of flatness condition. So I should also just mention equivalently, since this is a line bundle, first of all, because if you think about the dimensions of the fibers, if X has dimension n, these also do, and then the wedge product has dimension 1. Because, in other words, like this dz1 through dzn wedge product is a basis of the space of sections. So, since it's a line bundle, it being trivial is the same as there being a nowhere vanishing section. So there's a nowhere vanishing homomorphic quantum form. So that's a fairly concrete characterization of the Calabi-Yau condition. Obviously, since I'm not a physicist, we are not physicists, I cannot explain, well, Mohammed Khan is a physicist. I can't explain why the Calabi-Yau condition is what comes up in string theory, right? But the point is, okay, there's certain, say, anomaly cancellation. Things do not work out the way you want unless you have this special type of manifold. And so intuitively, for us, how do we think about the Calabi-Yaus? They're flat in some sense. There are actually a ton of different equivalent characterizations of what a Calabi-Yau is. Some of them are more differential geometric than others. You could talk, for instance, about the Ricci curvature vanishing everywhere. I'm not going to define what Ricci curvature is. But it is some kind of flatness condition. So, I guess on that note, okay, let's talk about a few Calabi-Yaus. Time flies. So, first of all, of course, dimension 1, maybe it's simplest, CY1s. So what are those? Okay. In dimension 1, what are the complex manifolds anyway? They are two-dimensional smooth manifolds. In other words, surfaces. These are Riemann surfaces, surfaces with a complex structure, and are classified at least up to homeomorphism, also diffeomorphism, by the genus, and the number of holes, or half the first Betty number. And I was hoping to give a quick derivation of why this is the case, but let's skip it. It's not hard to check that the only genus that gives you a trivial canonical bundle is genus 1. And this is the only Calabi-Yau. In other words, the Calabi-Yau curves are elliptic curves, which intuitively this checks out because after all, an elliptic curve, if we try to think about a metric structure on an elliptic curve, it's a quotient of C by a lattice. What metric do we put on it? Well, we think about the one induced by C itself, right? So it's a flat torus. So in dimension 1, the Calabi-Yaus are elliptic curves, which, of course, there's a lot to say about.
Does it have to do with the Gaussian, the integral of the Gaussian curvature against the R?
Yeah, that's one way you could think about it. Yeah, the way that I maybe was planning to, there's tons of ways you could prove that this is what is necessary for the canonical bundle, or necessary and sufficient for this to be trivial. For instance, it's a really quick calculation using the Riemann-Roch theorem. But yeah, I think it's kind of equivalent to say that it comes from the Gaussian curvature being 0. Yeah. Okay, so that's in dimension 1. We're trying to get a handle on dimension 3 ultimately, right? That's the goal, and that's what mirror symmetry concerns, at least in its original formulation. Dimension 2, I will not even write anything down about. Those are called K3 surfaces. we don't need them, so we're just gonna leave it at that. That's the name. And okay, so then the goal really is, what about CY3s? I guess I should also mention here that when I say classified, right, we want to answer the question, at least if we put our physicist hats on, like, apparently this is an important thing to think about. What is the space that we need to compactify these extra conventions? So the natural question is, what is the space? Or the natural question, then follow-up question from a mathematician's point of view is, what are all the possible candidates, at least, for that space? Because like, what the space actually is kind of a physicist question, right? Like, we are just concerned with what are all the possible Calabi-Yau's, or Calabi-Yau threefolds. But of course, to answer that question in any kind of reasonable way, we have to say, like, up to what equivalence relation. So at least in this dimension one example, up to homeomorphism or diffeomorphism, they are just the genus 1 curves. If we're trying to do things a little finer and we ask about bihomomorphism, in other words, isomorphism as complex manifolds, then there's a whole continuous family of these. There's, so just the key word here is the J invariant. So in other words, you can have, this is not necessarily a particularly, it's not too misleading a picture. The idea is that different tori are all diffeomorphic, such as these two, but the exact shape of the lattice that you construct this from does affect the complex structure. So, you might imagine, loosely speaking, like maybe a fat torus and a skinny torus. They're diffeomorphic, but there's something about them that, we're not going to get too much into different ways to interpret what a complex structure gives you, but it's more structure than the smooth structure, right? At least you can talk about angles and things like that. So these are diffeo, but not bihomomorphic. Anyway, I just mentioned that because ultimately, if we're driving towards this question of classifying CY3s, Calabi-Yau threefolds, we have to meet, like, what do we mean by classification, right? So we're really going to focus on, at least in this little story, up to homeomorphism or diffeomorphism, which is in some sense the easier question compared to categorizing up to bihomomorphism, which might have a lot more, you have different parameters you have to think about. Okay, so CY3s, that's the thing we've been driving at. So there's a lot of them. First of all, this is a much harder question than CY1s. So lots of them, even up to homeomorphism. So how might you try to get a handle on this? Again, this is the pseudo-historical part. I'm not like completely lying to you. You can look at various papers from the 90s, but I'm simplifying a lot. So what could you do, right? For lack of a better idea, think about what CY3s you know about, and just try to see what you can say about those examples. So actually, to continue, I'm going to have to take a detour now. So this is section 2. Oh, I didn't even label the sections. Anyway, now we have to talk about Hodge theory briefly. Like this. Okay, so again, I'm going to rather be extremely sketchy with this. The only thing that we really need from Hodge theory, as far as we're concerned for this, is the fact that, so if you're trying to classify CY3s, and you want to know, which ones are possible, at least from a topological point of view, one thing you could talk about is, for instance, the homology groups, or cohomology groups, like the Betti numbers. So you could ask which Betti numbers are possible for these. Maybe there's some kind of constraint. But these are not just topological spaces. They have more structure to them, so we could do better than that. And that's where the Hodge theory comes in. so I'm going to cut out several pages of what I wrote down and just leave it at this, which is that the fact that our X here, our Calabi-Yau threefold, is a compact Kähler manifold gives us quite a bit more information about its cohomology groups. So this is the Hodge theorem. So I have to say what this is. It tells us that the cohomology groups of X, whether derived or singular cohomology, they have this additional structure to them. They have a particular way you can break them up as a direct sum of subspaces, and this is called the Hodge decomposition. These, it's so sad how little you can do in an hour, actually. These are so-called Dolbeault cohomology groups, where basically, instead of thinking about acting on forms with an exterior derivative, you act on forms of a certain type with a derivative that is kind of takes into account the complex structure. So I should say what I mean by this.
And Alexander, if you
Yes.
want to talk again in 2 weeks, you can.
I think that might have to be what happens. Again, the mostly coherent part is rapidly becoming.
Maybe this is part 1.
Yeah, let's call this part 1. Where this is basically, it's kind of analogous to how you define the exterior derivative of a form. By this I mean a PQ form, which is something that's locally of the form. It's got P of these homomorphic parts and Q of these anti-homomorphic parts. Of course, we can take sums of these things and whatnot. So this is supposed to be, sorry, I shouldn't say F, I should say F dz1, no, call it dz I dz bar j. This is defined in a completely analogous way to the usual exterior derivative, except we just take this so-called Gertinger derivative J, where perhaps we have all seen this in complex analysis before, where this derivative with respect to z bar is, you can define it in terms of the usual partial derivatives, but it's the thing that vanishes if and only if f is homomorphic. Anyway, the relevant point to us is that we have this alternative differential operator. It takes PQ forms to PQ plus 1 forms. You can define a cohomology in terms of that in the same way you define derived cohomology. Except this somehow inherently involves the complex structure, because we have to talk about z's versus z bars. And when we do that, we can talk about, okay, these new Dolbeault cohomology groups. Again, these in some way see the complex structure. And we're saying the regular cohomology breaks up into this decomposition. This is a very, very useful observation for a number of reasons, but perhaps the one that's most relevant to us is that now this gives us a way of splitting up, refining the Betti numbers, the dimensions of these guys, into a sum of the dimensions of these guys. And these particular dimensions, it's just more granular information about our manifold. right? So that we can think it's a complex manifold. It has more structure than a smooth manifold, so we can get more detailed information than just what comes from the smooth structure. So from this, we form the Hodge diamond, just a convenient way of organizing this data into, so this is the dimension of these PQ homology groups. You arrange them into a nice little picture like this. So this is H0n all the way down to HNN. And all of these, so this is the dimension of H00, dimension of H10, and so on. And the point is that this bunch of integers, it tells us more, right, than just looking at X as a smooth manifold. And the reason that we want to talk about Hodge diamonds is that now we are basically poised to talk about at least one formulation, maybe the simplest formulation of what is this mirror symmetry. Right? So it's taken us 40 minutes to get to that point, but that's what it takes. Right? Let me pause here because I've just been trying to go a million miles a minute. Does anyone have questions?
So this is like if you change the complex structure, it's gonna change the numbers in there, but it's not gonna change the.
It could. It
change.
depends. It depends. Yeah. So if you look like these numbers are, if you have like a nice family, then they should be constant. But of course, you know, if you have like, yeah, let me just I don't want to get too specific, but yeah, they should be. It depends how you change the complex structure, right? Like if you change the complex structure on the same smooth manifold, then okay, then this relatively, even though this is a finer invariant than just the Betty numbers or the cohomology, like derived cohomology, it's still, you know, it's not a complete invariant for the complex structure, right? Yeah, does that kind of answer your question? Anyone else before we go full steam ahead to try and talk a little bit about mirror symmetry before the hour's up? Okay, so the point is, basically we've built up at this point, we're trying to talk about what can this particular class of manifolds, these Calabi-Yau threefolds, be? And we have this invariant, the Hodge numbers, these dimensions. So, for CY3s, it turns out that the Hodge diamond has a very particular form. It looks like this. There's various symmetries that are always true of this Hodge diamond, and without even mentioning them, this is what it always has to be for a Calabi-Yau threefold. And the important thing to note here is that there are only two parameters for us to work with, right? There's the H11, which we're calling A, and there's the H21 or H12, which we're calling B. And that's it. So we can kind of simplify our original question of what are all the possible Calabi-Yau threefolds to just what A and B can a Calabi-Yau threefold have. That will give us a lot of information. So, for lack of a better theoretical idea of what to do, what people at least started to do in the late 80s and early 90s was, okay, there's a bunch of known Calabi-Yau threefolds. Various examples, complete intersections in projective space and things like that. So, what are A and B for all of those? Make like a graph or something, right? Graph all those data points and just try to find some patterns. So, for known CY3s, basically, this is some of the stuff people came up with. If you look at, I'm slightly changing the coordinates here. Instead of A and B, I'm doing A minus B, A plus B, but of course that doesn't really matter. You can always reconstruct A and B from that. So first, this was in, I think like 89 or so. Let's double check. Yes, okay, so this was, among many other people, one of the names that keeps coming up with this stuff is Candelas. He did a lot of the things in the early parts of mirror symmetry that I will now tell you about in the last 15 minutes. So for, I'll say, a certain class of CY3s that are particularly nice, people were just like, okay, what are A and B for those? And maybe we can make some guesses. And it turned out to look something like this, roughly speaking. And in particular, some of the features that people noticed were, okay, well, maybe is B always more than A, right? Is this always negative? Is A plus B bounded, perhaps, right? So the various things you can maybe think about the structure of these Hodge numbers, but that didn't last very long. So I think in, let's see, was it 91? No, the very next year. So they extended to, they found more examples, right? And these were now hypersurfaces in so-called weighted projective space. Alas, we do not have time to talk about weighted projective space. So these are complete intersections. These are weighted projective hypersurfaces. And it turns out, okay, a lot of the things you might have guessed about this were, in fact, artifacts of the type of Calabi-Yau we're looking at. So now it turns out you do have many cases where B is greater than A, right? But, and now we can finally get to the first punchline here. One thing you notice about this particular class of Calabi-Yaus, what the A and B satisfy, is that it seems like for every point over here, you have a point over here. There's this left-right symmetry. And just a little bit of algebra shows that that's the same as saying for every Calabi-Yau with Hodge numbers A and B, there seems to be another corresponding one where A and B are swapped, where this is B and this is A. So again, I'm leaving tons out, right, about why people actually believe this is true from like the physics perspective and whatnot, and also even from the mathematical perspective, like there's many things we could say about talking about families of varieties, but anyway, just to give some kind of notion of what this mirror phenomenon is supposed to be, it looks like every one of these with an AB should be paired with somehow one with a B and A. And in fact, even when was that? This was another couple of years later, in 93, Batirev came up with tons of examples. So then, like, instead of thinking about things in a projective space or a weighted projective space, being looked at or subvarieties of toric varieties. Again, we can't go into that, but a more general class of varieties that includes projective spaces came up with hundreds of millions of examples of these. And basically what you get is just like a denser version of this plot. So it really reinforces our original conjectures that there is such a symmetry. And then later, this is Batirev in 93, toric varieties, basically. Okay, so it seems like, at least from an empirical point of view, there is this phenomenon, now we can actually state it, the first version of the mirror symmetry conjecture, and kind of the most like down-to-earth version. So mirror symmetry version 1. So for every Calabi-Yau with Hodge numbers A and B, so H11 H21 equals AB, there exists what we call a mirror manifold. Let's call this X, we'll call this X check, with H11 H21 equals BA. Okay. Now, I'm already being kind of misleading here. There's reasons that this can't be true, as stated. For instance, if H21 is 0 here, there can't be a Calabi-Yau. If H11 equal to 0, but at least for some class of Calabi-Yaus, like there's this observation, there's this phenomenon. You just have to be careful about it. But this is the original, or one version of the source of this idea, and a particularly noteworthy application, what really got people's attention was, and this is the last thing I'll say in the part 1, which took up the entire time. So I guess, okay, we can call this an application of this mirror phenomenon, which really got people's attention. Again, all this is happening in like the early 90s. Was, okay, so in algebraic geometry, one of the natural questions you can ask is, are enumerative questions. In other words, like, given some space, how many geometric objects, curves, surfaces, whatever, are there that satisfy some constraints? So in this particular case, the question was, so how many rational curves of degree D lie in a, let's say, general quintic threefold okay, just real quick terminology. Rational curve, I just mean something that can be parametrized by rational functions, essentially. Degree D is kind of self-explanatory. And quintic threefold, I mean defined by a 5th degree polynomial in P4. So you can ask this question. It's kind of a natural, I mean, there's many, you could come up with all sorts of different permutations of enumerative questions, right? Like how many curves are tangent to this and then go through these points and so on and so forth. And this is something that there are very classical antecedents. Hermann Schubert figured out in the 19th century the number of lines on a quintic, and which I probably should remember, but that was in 1975. This is Schubert. This is an old result. This is 1880 something. 6. And then to show you kind of how hard these questions are, it took another century for Sheldon Katz to figure out the case of conics on a quintic threefold. And that was like 609,250. Just saying this to give you an idea that this is actually, the complexity of this problem really balloons rather quickly and people had a hard time with it. So in the 80s, right, they just figured out the degree 2 case. And then there was this issue of, okay, what about cubics, rational cubics on a quintic threefold? And with, plenty of effort, a couple of Norwegian mathematicians came up with a result, with computer assistance and whatnot, some big number. So, and 3 was perhaps Stroma in 91. But, okay, so they came up with this, but string theorists were interested in this problem for their own purposes because basically you end up, when you try to do like this sum over hysteresis thing, you end up trying to count curves of this type in this quintic threefold is a Calabi-Yau threefold. And they came up with a different number, which was this. This is Candelas again, and a few collaborators. And Paul is also a 91. Okay, so, I mean, it's a math problem, right? It's algebraic geometry. So, like, of course, nope, no, this is actually wrong. There was a bug in their code that they used. And when they fixed it, they actually got this number. So somehow, using their heuristics, the physicists figured out the correct number. And not only did they do that, they actually found a generating function for all the NDs. Now, again, I'm sweeping a little under the rug because it turns out that there's a bit of interpretation you have to do there to know whether these actually are counting the number of rational curves in the way you want or something a little bit different. But let's just say, because we're being very excited here, nonetheless, it was shocking, right? Like that somehow or other they calculated this. Not only the n equals 3 case seemed like each next degree seemed, more and more difficult, prohibitively even. But all of a sudden they come along with this, one fell swoop. We figured them out. And what was the secret? I guess this really will just be part 1. But anyway, it's a nice place to wrap things up. Was this mirror symmetry phenomenon? So I'm going to then just talk a little for the last couple of minutes about, we saw one very, basic version of mirror symmetry, but there's many other phenomena that we did not capture in just this simple numerical version, right, where the Hodge numbers get switched. So I guess the last thing to say would be like other manifestations. Of mirror symmetry. And this will hopefully just entice you for the future, which is that, okay, so we just talked about the Hodge numbers, right, and the fact that, okay, it seemed like for every Calabi-Yau threefold with a certain pair of Hodge numbers, there's another one with those flipped. But that's kind of just the tip of the iceberg here. So let's say A and B. So these are manifestations of quite a lot more going on behind the scenes. Namely that, so these are, again, more kind of physicsy terms, that besides just the A and B, again, if you study more in complex geometry, you find various ways to interpret these things geometrically, and it turns out that this B, for instance, isn't just telling you something related to the third Betti number. It's also telling you specifically the number of, or at least linearly independent, like the number of complex deformations of your space. So this B, again being kind of vague, is related to the complex structure of your Calabi-Yau threefold. And likewise, this A also has a geometric interpretation. This is something related to the Kähler form or the symplectic structure. And people came up with all sorts of other mirror phenomena here, such as, for instance, the number of curves in, so let's see, on X, number of curves in X of a certain degree or a certain genus, so such as in this enumerative problem, was connected to something relating to the complex structure on the mirror, which are the so-called period integrals. This just means integrals of algebraic or homomorphic, let's say, differential forms over some submanifold. The point is basically to really not explain anything, but the way that Candelas and his co-authors managed to figure this out was this is a rather difficult problem, obviously, and by using this sort of duality, they transferred it over to, there's many classical techniques, as Professor Griffiths, he invented half of this stuff, be able to tell us about. There's many ways of dealing with this. It's a more accessible kind of problem than this was at the time, at least. So by on a different manifold, they were able to calculate some period integrals, and that's where those numbers came from. And then the final thing I'm going to put in this table, again, I'm just going to pawn this off to the most recent talk by Mohammed, and Lagrangian submanifolds on X are supposed to correspond to, in some way, homomorphic vector bundles, or really, what I should have, I completely lied about the scope of this talk, and we didn't talk about coherent sheaves at all, so that will be part 2. But the point is there's supposed to be this numerical symmetry that we observed is just the most superficial manifestation of some kind of duality between things that depend on the symplectic geometry of X and things that depend on the complex geometry of X check. So this mirror symmetry phenomenon, and then there's many other formulations of what this is supposed to be, is this duality between these two very different kinds of geometry. And let's see, I mean, we're already over time, so I should probably, that's a reasonably natural place to stop. But the point is, physics magic, they have their undefinable path integrals and whatever that we will hopefully figure out in this century. It gave us some really interesting things in algebraic geometry for starters. And this is kind of, now you, in principle, know what a Calabi-Yau manifold and whatnot is, and what this duality is, at least in the simplest case. I think I'll stop there. Questions?
One question.
Yeah.
So, if the third line over there, the number of curves in X, period integrals on X check.
Yeah.
So at the time that this was done, like
Yeah.
was that actually a correspondence, like saying, oh, this
Okay.
is exactly that?
So as far as I know, I think most of you should take this table to, at least on the whole, be conjectural.
Okay.
Right? There are many parts of this have by now been proved in certain situations. So, for instance, I mean, there's so many different directions you could go in, different versions of mirror symmetry, but a lot of this is known in cases of certain special X's, right? So for, I don't know, one of the earliest ones might be if X is, well, we were talking about Calabi-Yau threefolds, but a similar thing applies to other dimensions. People proved it for elliptic curves, people proved it for certain kinds of Fano varieties, which are not Calabi-Yau. You have to do something different here. But the point is, it's a big patchwork. There's many cases that have been proved, cases that have not been proved, right? So in general, it's not really, what I was hoping to get to overly ambitiously is the statement of like, Kontsevich came up with a way of, one particular way, of formulating this as some kind of structural correspondence between the symplectic geometry in X and the complex geometry in X check, which is not proved yet in full generality. But there's a lot of cases that are known. Anyway, so at the time, I think it's, don't 100% take my word on this, but I think it was basically, no. At the time, it was basically a physics heuristic argument, right? It was not mathematical proof. Yeah, a few years later, actually, Giventhal and some other people did prove that particular case and confirmed that the calculation is
that
correct.
thing in there is correct.
So this has been proved. At the time, it was not. Like at the time, it was kind of a heuristic argument that happened to agree. Well, actually, I should be more careful. They came up with this number. These guys, once they fixed their computer issue, like the programming bug, they came up with the same number. And then not too long after, some people, again, Giventhal was one of them, but there may have been others, proved at least mirror symmetry in the relevant circumstances. But in general, as this correspondence between symplectic and complex, there's much still remaining to do.
And that generating function for the NDs, that's proven now, or?
At least, so the tricky thing is, and this is the part, you should talk to someone who knows more symplectic geometry than I do. These NDs basically, they are, I didn't use the word, but this number of curves is really, you're calculating Gromov-Witten invariance. And those are, at least in some nice cases, equal to this curve count in like the naive sense. But in general, they could be different sometimes. So actually in this particular case, as far as what Candelas and his co-authors came up with for this, I don't know for sure whether that is, I think it's not necessarily established that those are all the like literal curve counts in every degree, but maybe someone else knows.
There's one that Kontsevich, I think it's a recursive formula.
Yeah. So there's Kontsevich came up with it's kind of related recursive formula for the number of degree D curves through, I think it was 3D minus 1 points in the plane, using some similar ideas. But I don't know much about that. And that is known, like mathematician known. Right?
Trashing Mohammed, man.
No, that's the thing. That's the thing. Like, this is incredible stuff, right? Like,
That's awesome.
right. We're just trying to, catch up.
Yeah.
Really. So, makes me wish I knew more physics, but anyway, here we are. Any other questions?
So, I'm wondering if similar symmetries exist in other dimensions. So
Yes. Yes, they do.
For K3 services, the first line maybe doesn't make sense because you don't have enough wiggle room in the
Yeah, sure. So the relevant thing, and this shows how little I know. I'm not sure what the corresponding thing would be for on like the Hodge number level for dimension 2, but the more general correspondence between the symplectic side and the complex side, which again, there's a way to make that somewhat precise. That's the homological stuff that we didn't talk about yet. That definitely extends to other dimensions. And like one of the first cases that actually got proved rigorously, like on the math side of things, was for elliptic curves, for instance, for dimension 1.
And does it go up in dimension 2?
I don't really know anything about that. In principle, probably, yeah. People have also done extensions of this stuff to non-collabial cases, but then the mirror has to be something more exotic. Like it's not necessarily a... So for this case, for CY3s, we're basically trying to find another CY3 that is the mirror, and you can also talk about what I was hoping to completely naively get to was talking about the mirror of P1, which obviously is neither three-dimensional nor collabial, or it's not flat in any sense. Right? P1, after all, topologically is a sphere. But we could still make sense of like the mirror of P1 in some way by constructing some, we'd have to get into what this means really, but there is a corresponding structure on the A side which reflects the complex geometry of P1 in some way.
Can you say the mirror?
Okay, so one version of the mirror is basically, so like you have P1 on the B side, and so it's again, you have to look at something that's a little bit, a different type of object, but basically, again, one interpretation is you take C star, or Z with the origin root, punctured plane, along with, you need a little extra structure to make it work. This is called, the term of art is Landau-Ginzburg model. It's just a function on this variety, complex valued function. In this case, it's a Z plus 1 over Z. So there's some ways to basically start with this function and do some calculus essentially, like look at its critical points and draw some curves connecting them, and then do all kinds of stuff with the intersections. And the nice thing is in this low dimension, the symplectic stuff you don't have to think about symplectic geometry too much, because like in dimension 2, real dimension 2, symplectic is like the Lagrangian submanifolds are just any curve and so on and so forth. But so you can draw some nice pictures where you just like have like a surface and you can draw some curves in between anyway. None of this is going to make sense if you haven't seen it before. But this so-called Landau-Ginzburg model is, at least in one interpretation, the mirror of P1. That's what ideally we would get to if we had 3 more hours.